Uncertainty threw me off for a minute.
Yeah, yeah. And then like, I honestly had no idea with the HTML and stuff.
The D3 thing where he was just trying to have you draw the SVG.
Right, yeah, it was like, and I drew some rectangles.
Yeah.
So, that's good.
I'm pretty sure I drew them right. As long as, well, that's another thing too, is like, with the bug, it probably doesn't work. Is that count? Like, am I supposed to just draw like?
That's the other thing I was like, so if we don't fix the bug, should we just draw the bug version of the thing?
Yeah.
We sit there and say smart aleck is like, well, technically that doesn't work. I just wrote that in there.
There's probably good points for it. I don't know.
But yeah.
Well, not worth the full 10, but it's worth it.
Yeah, I agree though, that the question is a lot easier than more technical.
That's what we studied for, right?
Right.
That's what we were like.
Not the D3 part.
Right.
Just like, I don't know, like they could ask 100 different questions about detail, and I might get any of them.
I totally thought the problem was going to be difference between data and data. Yeah, that's how I was thinking about this. Like, there's no way you guys like with selections. That's too easy, right? And so I didn't study that. There's going to be so many with selections. And there's something that was hard with selections.
Yeah.
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 Reach out to you.
Yeah. Maybe it might work like 10% of it.
Yeah, it's worth like that sounds right.
Yeah.
Oh,
It's pretty.
So that's not
Yeah. I don't know. It seems like you have
might
some
be
exams.
based on.
It seems like you're liking the exam in the first place. So.
It's the first written exam I've taken in a long time.
Yeah.
Some experience. Right? That's it.
Yeah.
How are you at home?
About after the first one. I got a long night. Yeah.
I stayed up till 4:30 last night. Yep.
That's bad.
I mean, it was like good time because I was like actually sitting before stuff. Yeah, and so it wasn't like I wasn't
Yeah, I forgot I can write at the end. Okay, I didn't see you guys.
I'm so sorry, I just started to say I'm going to come with this.
You're good. I got it.
Hey, how's it going? Yeah, go for it. Yeah, absolutely. You were in the song review. Maybe that's the guy who initialization of you know what the graph there is, right? It's like
Is it good?
yeah. So there's a type of I was actually project like a called that was on top of that I was doing focus on the loss. It's pretty it looked big. Like maybe some water. It's sure it's there, but it's like yeah, I just it's something that comes from as much as like what's like
so your final loss after is a function of not just initialization, but it's also the learning pattern, which can also be reduced. So you cannot say that your loss is only to determine how random you got it.
And then you basically get
That's
the
the,
It's not the Asian one, it's actually
there
the
was
base.
which,
has its pros and cons.
No, I didn't tell you. I was just asking for your thing.
was cold
One minute is your second parameter.
Well, through
So if you have these parameters, irrespective of the loss, that's the effect the insect. So you may likely use less than
I could not get a secret. I was trying to do that. And then everyone's like, oh, he's bringing it to
so you may like high layer network may give you a lower loss because it has
I guess I really
loss alone, the loss is not the size of so don't confuse the size.
I think we could potentially do it like
Yeah, so generally,
We don't really expect a quantitative or quantitative.
let's say
You can take this.
That's what happens when you have it like for one. And let's say you had 3 different molecules. Part of the problem with that is
I'm sorry.
Oh, that's fine. How are you?
all of these patterns inside of it, they're all
So then like
well,
Somebody was asking. No, I'm sure it's a busy time. Homework's due. Thank you. Okay, let's get started. How's everybody doing? Good? Good, thanks. How's the homework going? Like a bunch of people have turned it in already. Like, that's great. But yeah, it's not due till tomorrow at midnight, so it's all good. I'm gonna be here afterwards if you want to ask questions. Hopefully you're making good progress and not getting too stuck. And hopefully you're getting help from the TAs as well. And they've done a great job. I appreciate them. All right. Any questions before we get started today? Yeah. Back there.
homework 1 has been graded now.
Yeah.
If we have questions about that, should we talk to TAs?
Yeah. I talk to TAs. If you send them an email, figure out maybe which one of them graded yours. Might be the best, but there's a rubric that they've all used. So, yeah, so anybody should be able to answer the question. Yeah.
So I noticed in the con 2D when you start to do the classes, there's like this dilation, like
You mean like in the PyTorch libraries?
Yeah.
Yeah. We will, let's see, do we cover dilations? I think we do cover or maybe you did cover dilations in like the third lecture on the history of CNNs. Anyways, I can't remember, but dilations are something like the following. You know how our filters are always like compact in the sense that it's always the pixels right next to each other? Dilated filters aren't like that. They kind of spread out. There's like space between the pixels, and there's a lot of ways to define that. But so it. Yeah, I think you can think of it as having like a fixed zero weight of like a larger filter. Yeah, but the idea is that you can like for the same number of weights, you can cover like a larger number of like a larger area of pixels, but at the expense of not having a weight for every pixel. But since you're striding, you're going to eventually cover them all. You'll have made some convolution with all the pixels. Yeah. PyTorch documentation is really fantastic if you dig in. There's usually links to papers and things like that. I mean, maybe not on the dilation, I'm not sure, but one of the really great things about PyTorch library. And always Google's right there. Somehow Google has the answers always. a little machine learning. Okay. Any other questions? Good questions? All right, so we're going to just get back into this. So remember, we were talking about object detection. We talked about Rcnn. It was this kind of crazy thing where we were forwarding these proposed regions through a convolutional network. From the features of that convolutional network, we were training a regression head that was predicting the coordinates of a bounding box, and then also a classification head to say what was in that image. And we said, oh, that's slow, there's problems with it. So we try to make these things faster. So the next one was appropriately called fast, Rcnn. It's very, very similar, but there are a few changes to it. And we started talking about this last time. We're going to finish this today. Then we're going to do all of Lecture-14 as well, but that one's a short one, it turns out. So we should be able to do it all if I don't just sit here and ramble the whole time, which I'm apt to do. Anyways, so the difference here was that we are going to forward the whole image through a single convolutional network. And then instead of going all the way to like the fully connected layers and just get 4,096 features, we're going to stop at a particular feature map. So in this case, if we were looking at like a VGG 19, we're going to stop at COM5, and there we are going to apply the region proposal method. So remember how there was this, we made this kind of mention of a thing we didn't describe, but it was like you could give it an image and it would propose regions of interest, places where, I don't know, like it seemed like the statistics of the pixels suggest that there is an object there. So we're going to do the same thing here, but we're going to do it deeper in the network. So it's going to be on kind of this more abstract feature map, these features that are deep in this network, but we can still kind of do the same thing. It's going to still work in the same principles. And you might think, like, how does that work? Well, once you spend enough time with these things, you can, you'll see that, like, even in layers like this, there's still some spatial structure that is consistent with the original image. As you get higher and higher, you're integrating more and more of the region, more and more of the image, together into single pixels. But still, there's some kind of, there's some strong correlation between those, and so you can do this kind of thing. And then there's this need to do this, to do some kind of reshaping so that we can know what to expect coming out of, for each region. We can have some kind of expected shape so that the rest of the network can work with it. And this idea of what's called ROI, and ROI here is region of interest, not return on investment or something like that, is region of interest pooling. And the idea is fairly simple, but what you do is so this is what we saw before. This is like, you know, that the ComNet, and we're taking the feature map out from, say, the Com5 layer. So it's going to have some sort of features. This may not be square due to the fact that, you know, we might have a non-square input or something like that. But the idea is that we want to make this square. So the way that we make this square is we simply, you know, whatever is the actual size here, you know, in this case, like in this particular example, so you're putting numbers of 20 by 15, 512 channels, that's the depth of the feature map, the 20 by 15. We want to say, well, whatever that is, we want to make it 7 by 7. And the way you do that is that basically you sort of, you know, you take whatever this extent is and divide it into 7 columns, 7 rows. You're gonna have, you know, within those that sort of like that coarser grid, a number of pixels will be overlapping in that grid, and you're just gonna do a max pooling where like that's kind of your, like the pools are defined by this more coarse grid. And then you're just gonna replace, you know, whatever was there, kind of, you know, here, the max pooling, that max feature would go here, and now we have something that's 7 by 7. So now it's of the right size, or it's of an expected size. I don't know if it's right or not. That's the fun thing here, right? Like nothing's actually right or wrong. It's like quantum mechanics. It's like it's in many different states at once, and maybe it'll work, maybe it won't work when you measure it. Who knows? But anyways, so now you do this, and then you that's now that your ROI pooled features, and we're going to pass that to fully connected layers for the rest of the network. So we get these fixed layers. We reshape those. It's in the expected format. We pass through fully connected layers, kind of like we've seen all throughout the convolutional networks, except for these fully convolutional layers or networks that we were just looking at last lecture. And then from there, we're going to have 2 heads again. We're going to have one for classification and one for the bounding box regression, for the coordinates of the bounding box. There's going to be losses for each of those. We'll put them together. It says multitask loss and loss, and we're going to optimize that. And so we're going to that's the computation graph. We back propagate through all of this, and so in some sense, this is a lot more. There's a lot less computation going on here than in like plain vanilla Rcnn, because we've only forwarded just one, just the single image through the network, through the convolutional network here, and not all of the patches, all the 2,000-ish proposed regions, each one forwarded through the convolutional network. We did this once, and we moved the region of interest, the region proposal to here, and that's just way more efficient. Only one, pass through all these convolutions, and then the rest of the network is all connected together in such a way that we can back propagate, and that's how this is done. That's the difference. And what's really fantastic about this is that this becomes way faster. So you see Rcnn up here in this plot. Training time. This is inference time. So you see 2 numbers here, red and blue. The only difference here is the 2-second difference essentially is just what it takes to do the region of interest proposal for Rcnn, for any of these things. Remember, it still exists. It's just whether you do it on the original image or you're doing it at the Com5 layer. There's something here called an SPP net we're not talking about. Here's fast Rcnn, and you see that training is changed by a factor of 10. It's basically an order of magnitude faster, and it's even better than that at inference time. So it's got this. It's performing roughly the same. In fact, it's a bit better because things the whole network's a little bit more end to end, and but it's way faster to use, and so it's appropriately named, I guess, fast Rcnn. Okay, so before we move forward on this, does anybody have this feeling like we could do better? And if so, where could we do better? Does anybody like not like this whole like region, like you have this sort of offline region proposal method that has to be used? Is that bothering anybody? It's bothering you. Good.
Is that another deep learning?
No. This is just like kind of this is just, you know, off the shelf some kind of thing that detects blobbiness in images and proposes regions. So if it isn't bothering you, I want you to like at the end of this lecture feel like it should bother you, because like all like, you know, in these last 10 years of you know, tremendous deep learning progress, one of the main themes of it is you know, going from, you know, the original architectures and things like that to that well, you know, oftentimes just, you know, they work, but they sort of have these clunky pieces that make it so that the whole thing is not just one large computation graph where you're training the whole thing end to end. And this is one of those examples where you have this like offline region proposal thingy that has to happen. That's out of the network. So we should do something about that. We should put that into the network. And that's what we do. And guess what it's called? Oh yeah, sorry. This was the motivating question right here. When we're this fast, inference time is dominated by the region proposal thing. So we should be getting rid of it. So how do we do that? Guess what it's called?
Really fast.
Really fast is a really good guess. It's faster Rcnn. Faster Rcnn, and this is a pretty common, you know, even this is, you know, this is fairly old, deep learning wise, coming from 2015, but this is a pretty common architecture to see still. We'll look at a couple of other ones that have, you know, many generations of them that are also used, but faster Rcnn is pretty much a you know, like a backbone architecture, or like a common architecture anyways for the object detection. So the only thing that really changes here, we do everything the same, except instead of running the region proposal method, whatever this goofy thing was offline, we just say, okay, we are going to have another convolutional network that's going to be that's going to go in here right here, and it's just going to like predict a whole bunch of bounding boxes. So instead of it being from some offline thing where we get all these coordinates, we're actually going to have a network that suggests all the coordinates, and it's going to be learned. Those operations are going to be, you know, parameterized by weights, and it's going to be part of the whole. It's going to be part of the whole network, you know, supervised by the classification loss and the bounding box, the final bounding box regression loss. And so we're going to, when we train this thing, we're going to back propagate through this thing as well, and everything will be learned end to end. Yeah.
So does that mean you have to put in your training data is going to have boxes on it?
Like to supervise this piece right here?
Yes.
No. This will output boxes, but like how good these boxes are is actually going to be supervised by these parts of the loss, right? Like you know, like the choices of these boxes are going to be parameterized. There's going to be weights that produce them, and it's going to be the signal, like how well we do on the whole task. That's going to that's going to supervise this. So yeah, so
all the training data, they don't have any boxes. It's just
well, it does, right? Like the training data always has had that, right? That's what these losses have always.
Oh.
Yeah,
Oh.
yeah, exactly.
Oh, I see. Okay, thank you.
Yeah. So anyways, so the whole thing's supervised end to end. There is a version of this where you can take the as training data, the actual proposed, so you know, like this offline method that we keep maligning, you can use that as you know, it produces 2,000 regions of interest. You can use that as an additional loss to supervise where these things ought to go at this point. So we have two additional heads and losses from from this layer right here, and we then put those all together and optimize the whole thing. And yeah, so now it's all end to end. The good part about that is that we no longer have the requirement of running this region proposal thing for every image. So what this is like, I've been talking about this common theme. What that means is, like, at some point there still is a cost that has to be incurred for this, but it's at training time. So like you amortize that cost, in training, meaning that, like that extra time sort of was taken up here, but that's okay because at test time, like since we moved that time, that complexity, that cost here, it's no longer at test time when we're running inference, and so that's much faster. And this is very much like the sort of the like the common reason behind end-to-end training is that you want to amortize all the costs as much as you can during training, over your training set, so that test time is as fast as it can be. Make sense? Yeah.
So does as it's learning this and training, does the cost decrease at all, or does it just remain the same amount of cost the whole time?
Like the cost of generating these proposals. Yeah. So like in the example where you're actually supervising these things with the proposed regions from that region proposal method, yeah, that cost is incurred during training, right? Like you still had to produce, you had to run that algorithm, right, so to speak, to get the whether it's inline or whether you did it like a kind of pre-processing step or something like that. It had to be done, but it was all during training. And the thing about training is, like, we don't care sometimes we don't care how long training takes. Like the idea is, like, we're going to train for as long as we need to, so that when we're done, we have the best model we can possibly have in terms of performance, both in terms of, like, minimizing loss on the tasks that we care about, and in terms of performance, like cost of inference, the cost of running an image through, forwarding it through the network. And so, because when we do that, we don't, this thing is trained so that it just produces the right bounding boxes. It doesn't have to run that region proposal. So all that cost got pushed to training, and now it doesn't exist at test time. It's just part of forwarding the image through the network. So it's pretty cool. And this is like a really common thing. Like, a lot of stuff is like this. Right now, there's a lot of research going into, like, how to search really complex spaces, like chemical space, like molecules, right? There are very large numbers of potential molecules, that one might think of using in a medical setting. And drug discovery is like you can think of it as a task of searching that space for a molecule with the right properties. But at 10 to the 60 drug-like molecules, you really have no chance of brute force covering that space. So how do you appropriately search that? Well, one of the really cool, like, research directions right now there is to sort of amortize a lot of that search into the training through some pretty cool, like, reinforcement learning ideas. And we'll talk about reinforcement learning at the end of this. But anyways, it's just a kind of a very common thing. Yeah.
For the ROI tooling,
yeah.
What's happening there? Is it literally just the proposal network and feature mapper being added, or like is there trainable parameters and those yellow arrows?
Yeah, I mean, think of this as like the computation graph. So, like, this is just like fast Rcnn, but instead of the region proposal method being run at this point, the network just like actually produces all of these bounding boxes. Like it's like part of the prediction. It's part of the computation graph where it produces all of these, and then each of these gets ROI pooled. This one right here, because this, I mean, like, just the illustration here is, this is just like the mask of. Think of this as just like the thing that contains the regions of interest, like all the potential bounding boxes, And this is the thing that has like the feature map, and now you're combining those two things together here. That's all.
So the CNN outputs that region for the map?
Not the CNN. The CNN produces this feature map, and then there's these are just other parts of your network.
Okay.
And this is producing these 2,000-ish. Just think of them as like, it's like a list of 2,000 coordinates.
Okay.
That's what this thing is doing. And then you're combining that with this to give you your regions. And then you do the ROI pooling here, just like we did before. Everything after this is the same as with fast Rcnn. Yeah, good question. Okay. So Rcnn, fast Rcnn, faster Rcnn. Is it faster? Yeah, it's way faster. This is test time speed, and notice that this was we saw this already. This was 2.3, but remember, roughly 2 seconds of that was the running of the region proposal method, and so now this is just 0.2 seconds, so it doesn't have. Essentially, we just cut out that cost. I mean, I guess it's a little bit faster, but yeah. So we got rid of it by making that a differentiable operation within the network, so that we could back propagate through it, learn the parameters of it, and amortize the cost of that during training, and so that we don't pick up that cost during test time, at test time. Make sense? Okay, cool. There are other things that one might do here. Remember we talked about so that the additional task of doing instance segmentation within each of the bounding boxes of like where the actual object is within that bounding box, right? The bounding box is kind of this crude approximation of like where is the object. You might actually want to know like exactly the pixels of which pixels within that bounding box correspond to the object. So this is an additional so mask Rcnn is an adaptation of faster Rcnn where we take the regions of interest, right? These are our bounding boxes containing objects, or at least what the network thinks contains an object. And what we do there is very similar to what we saw in like the ROI pooling. We sort of turn these into a feature map of some fixed spatial dimensions using exactly the same kinds of operations that we already saw. And then within that, we basically do what do you call it? The semantic segmentation that we already saw, where we now have a class vector at each of these kind of coarse pixels, right? So remember how when we did semantic segmentation, every pixel was classified, and that's how we were able to do all these pixels are a cat, and all these pixels are a grass, and so forth. So we're going to do exactly the same thing here. And so, you're basically, you can think of this as like predicting where the class is and where it isn't. It's something like a mask that one would apply over the top of this. That one, it's a mask at this sort of coarse level that one can then apply, backwards on the original image, and do this segmentation. So it's just it's combining, faster Rcnn, or just Rcnn, that family of architectures, and the ideas from semantic segmentation, where we're doing semantic segmentation for each one of these predicted bounding boxes. And of course, you have to have labeled data for that as well.
Why not just use straight up semantic segmentation?
Because think about how really costly that is, right? So the nice thing about this is like you're just learning a mask for like you can think about it, so it is for each of the masks or each of the classes, but the idea is that you have only one object within that bounding box. So instead of like having to classify each one of these pixels, you only are required to classify just the pixels within the bounding box, and then you just know that there's a single object. So this makes sort of like conceptually this makes it easier to work out the mask. I mean, you still are making a prediction of which class is there, but you know there's only one. And anyways, so it's far more efficient because you're only doing this per bounding box. Now the bounding boxes can overlap, and I guess if there's like tons of overlapping objects, this could maybe be like if they cover the whole image, like this could be more costly. But in general, there's only like a few objects compared to the number of pixels, and it's far more efficient. So anyways, that's called mask Rcnn, and it's pretty good. This is the typical kind of thing that you would see from mask Rcnn is you get your bounding boxes, you have some prediction of what kind of object is in there. You can't really see that probably at the scale, but this says person with a 100% 100% probability. This is person with, I can't read it, actually 0. It's 1 again, so it's all 100%. This is bottle with 100%, bottle with like 0.99 or something. But it's not only is it drawing the bounding box correctly, correctly classifying, but it's also you have the mask for that correct class, and it's showing you the right pixels. It's now divided up your image in this way. So it's not quite semantic segmentation because we don't have we don't have something for like the ceiling or the walls or these window things, these window sections over here, right? That's not part of the task. The task is simply just the objects that are in there. So it's super cool and pretty useful. And like this kind of thing is used commercially, like all over when there are natural images. Like when you see some I don't know, some application, maybe some startup, or even like a lot of the companies, like a lot of the social media companies, when they're talking about analyzing what's going on in images, this is very often the kind of network that they'll be using. Is because this gives you a lot of information on what's in the image, right? All the objects, choose whatever classes, as long as you've got the labeled data, all the objects, likelihood of that object being in that bounding box, and then in particular the pixels that are associated with it. So pretty ubiquitous, lots of commercial applications here. Some good, some bad, but lots of commercial applications. There's lots of other things you can do with this kind of thing. One of the interesting things is like pose estimation. So if you have a little more data where you have these sort of key points about where the joints are on these objects, it's like oftentimes if we're talking about people, we have key points for like the face, joints like the shoulders, elbows, waists, knees, things like that. Then this same thing, the same kind of architecture can learn not only to segment out these pixels, but also correctly predict where those key points are. Basically, it's again classifying particular pixels as having a key point or not. So another one of these kind of really interesting ways in which deep learning is developed. The architectures pretty much stay the same. You just sort of add on heads for predicting other things, from the information that these architectures are extracting. So it's already got all this information for like that this is a person and these are the pixels. So you might as well just use that same information, those same feature maps that have the information to do this, to then like pick out particular types of pixels within that object.
So that'll be like after the fully connected layer.
Well, this is in masked Rcnn, so it's like another, for each of the pixels, it's like another supervision, like another head supervising like a class of that pixel. Like is it a key point or not, and which key point is it? So basically, like when I say key point or not, it's not really like that. It's like, am I a eye key point or a shoulder key point? And then one of the things you can classify it as is not a key point. Okay, so it's pretty common to use that. It's pretty common to just use pre-trained ones, and you know, in commercial applications. Most model zoos, you know, in your deep learning networks will have something like that already that you can use. There are other object detection architectures, though. The most well-known and has had a number of like iterations done on. I think YOLO is at generation 7 or something like that right now. Pretty sure like version 7 just came out pretty recently. YOLO stands for you only look once, and the idea here is that you don't actually have region proposals in the sense of like, you know, either having this method having this method, you know, outside of the learning that does it, or some part of the network that proposes it, but you have a kind of like heuristic for how you start with a well-chosen set of like bounding box starting points. They're called base boxes, and then you basically are just learning to you know, either eliminate them or adjust them so that they're actually, you know, appropriately covering an object. So it's a little bit like the thing that we poo-pooed at the beginning, where it's like, you know, sliding a whole bunch of different bounding boxes over the image, but it's not really that. It's more like smartly choosing a much smaller subset of those, and then figuring out which ones of those we should keep, and then how to adjust them to cover objects. So I suppose there's still kind of like regions that are proposed, but it's not in the same spirit. It's just like a fixed set of these things. SSD is another version of this. Single shot detector is what that stands for. Yeah. What's interesting about this is that you really, when you look at this whole thing, you really just have one big convolutional network. Anyways, that's that for object detection. We spent a lot of time talking about the ImageNet competition, like the classification competition, but the ImageNet group had, you know, there were lots of different computer vision tasks in that competition. There is an object detection one, and you can see here's 2012, and object detection wasn't used, or a convolutional network wasn't used to solve the object detection problem. But in 2013, you had Rcnn, and it wins. The measure is different. We're talking about this mean average precision is about how we appropriately are covering the bounding boxes. Like, you know, the bounding boxes that we predict are, you know, how well do they cover the actual bounding boxes, the ground truth ones. But you can see that, you know, 1 year later we get a convolutional network for doing detection, and then very rapidly, you know, this becomes very, very good until it's, you know, very similar to classification. Convolutional networks are like the best, or as you know, getting as good as humans. Yeah, just you know, people have the data sets, and so these are like these different. So this is like Rcnn. I can't remember what this one is, but this is like the fast Rcnn, and then improvements to it that were actually part of the competition. And then you don't have mask Rcnn until 2017, and like YOLO and stuff like that. But the whole point is to show that, again, like deep convolutional networks sort of just smash this problem wide open and allow for just much better solutions. In fact, you know, getting to the point where they're performing like humans on the tasks. Yeah, there's all kinds of open source implementations of this stuff. All right, so we should be able to get through lecture 14. Questions on that before we move on? This is going to be the second part of object detection and segmentation. We were supposed to finish it last time, so this was the recap, but you know, we just did the recap. Any questions on Rcnn, faster Rcnn, mask Rcnn? when you say parts here, what do you mean?
Like, you would train the masking part that comes after. So you draw the bounding boxes, and you have your foster Rcnn do that. And then you have a mask on top of that, right? After you get the bounding boxes, you apply the mask method, right?
No. Let's see. So like, if we go back to this, you have two losses. One for how well we are, predicting the ground truth or like the actual bounding box, and at the same time, how well we are classifying the object that's within that bounding box. So it's all being done at once, end to end. And even in mask Rcnn, it's the same thing. We have we're gonna do like we have this is just like that, the one, like here's all our predicted regions of interest. There's still going to be the parts that are going to predict like figure out if this is the right bounding box. We're going to have that loss, and then the classification it's actually here. But we're going to have one more loss that's going to be a loss about like, are we getting the object mask correct or not, right? Which is essentially like a bunch of classification losses for each of the pixels within that bounding box.
Okay.
So it's all being done at once. Like every single training image that comes through here, the loss is basically indicating how well we're doing in all, like in here in all three of those tasks: getting the bounding box right, getting the classifying the object correctly in there, and then getting the pixel mask correct.
And then we combine those losses. Like, would they have different separate heads for calculating?
Yeah. So you have all. Yeah. Think of these as all have separate heads.
You just add them together at the end.
Yeah.
And
there's usually hyperparameters that are weights, right? So like, if there's three losses, like in this case, you might have one just that doesn't have a parameter that you multiply by, but you multiply the other two by some scalar coefficient, and it's just a way of weighting it against all the other ones. And the higher it is, the more weight you're giving it, like the better. Something like that, yeah. It's a way of specifying that. Now you have to be kind of careful because each of those losses are have a certain units that they're measured in, right? So like cross entropy is measured in information units like nats or bits or something like that. Whereas bounding box, this is like an L2 distance, so it's more like a unit of distance. And so those parameters not only are something about the weighting, but they're also a conversion, however you think about it, a conversion from one set of units to the other. And that, so like there's like the bringing the different units onto the same scale. And then so it's almost like there's like two parameters here, but it's all one parameter, and it plays these two roles of bringing it onto the same scale and then expressing if it's like more important or less important. So if you have like a bunch of classification losses and they're all measured in the same information units, then the parameter just is like, am I upweighting or downweighting this task? But if I'm combining regression and classification, my coefficients kind of have this dual role. Yeah. Again, you just futz with them until they work.
Is that also how, because we had multiple heads in way back in Googling that. Did they also add them at the end?
Yeah, you basically always just add losses together with these coefficients that express the weighting and then sometimes the conversion of units.
Right.
Of the loss, yeah. Yep. And they're just hyperparameters, so guess what? Like all hyperparameters, you want to tune them somehow. If you were to do this appropriately, it would be proper cross-validation, but oftentimes these things can be very expensive to train, so it's not proper cross-validation, but you like look at yourself in the mirror and you say, but if I could, I would have done cross-validation. And then you just make yourself feel better about that. I mean, obviously you do some retraining, but you don't. It's really hard to do like full kinds of like grid cross validation when there's so much data. The networks take so long to train. Someday, that won't be the case for many of the networks that we've been talking about today. Like they'll seem very, very small and they'll train very, very fast. But yeah. Okay, so yeah, so you can do totally cool, amazing, wonderful things with this. I'm telling you, like so many. If you know of a company, whether it's one of these massive like social media companies that do a lot of things with images, or just I don't know, like some local company that's what was it that Professor Henderson was showing us? It was like figuring out where the like the orange construction cones were, or like the canisters or whatever those things are. Like basically, like it was something that like was driving around and figuring out where all those were. Those applications are just using these networks, and they're just it's like you fine tune them for the task. So like if it's just to find these orange construction barrels wherever they are, then you don't need it to like recognize every object. You just need it to recognize that object and like where it is in the image, and then obviously combine with some other information like this picture was taken at these GPS coordinates, and now we can go pick it up. Maybe we could send an autonomous vehicle to go pick it up. Humans don't have to do anything anymore. Just learn how all the robots do things and just smile and drink whatever. But this is like the core of it, and it's super powerful and it works super well. Mainly because there's just amazing data sets for training on it that have people have spent so much time labeling them. What other things can you do? Remember we talked about captioning at some point, and like early on in the class we kind of looked at examples where you can do the same thing here, where instead of captioning like the entire image, you can caption sort of each bounding box, and it works almost exactly the same way. You just need to have another head, which is turning some representation of what's in that bounding box, using that as input into another part of the network that can produce text. And we haven't really gotten into any of that yet. That's going to be like the next big sections. We're going to look at models for dealing with sequential data, so language being one of those, but there's a lot like any kind of time series data is sequential, and there's lots of other examples. But that's the idea here, is that you've learned to do these networks learn to do all these really cool things. It's learned a really information-rich representation of what's in this bounding box by doing these other tasks, and now it can be also trained to do things like do this captioning. Again, as long as you have the appropriate kinds of training data. I'm not going to really get into the details here, but the idea is very much as you'd expect. You're going to get something that looks very much like what we saw before in terms of the just what like the faster Rcnn and getting these regions and what they will do. But then you're going to have, from those features, you're going to have some kind of network, and this is an LSTM. We're going to learn about this. This is the kind of sequential model, and it's going to produce these possible captions. And so you get like all this really cool stuff. And this is actually a bit old at this point. Like there's not in the sense of like this is like an old task, but there are much better systems for doing this kind of thing. Okay, so how is this done? Like, where do these data sets come from? Well, one of the most well-known and the one that's used for many of these commercial applications, unless you have you or your company or something that is invested in producing these data sets, is something called MS Cocoa. So MS for Microsoft, and then Cocoa is the name of this data set that has, again, it's all natural images, but it has a whole bunch of labels. Not just the label of like what object is here, but it has you know, object segmentation, so these pixel masks. It has, you know, the bounding boxes with what type of object is in this bounding box. It's got, you can see this, it's got a ton of pose estimation in here. So like the key points for the like people objects in this. It's got a variety of different kinds of masked objects. Lots of different object categories, stuff categories. And then for a lot of the data, some large subset of the data, captions per image. So in this case, 5 captions per image. And you can see the data set has like 250,000 people with key points. So these things are super expensive to produce. They require tons and tons and tons of like people hours to do it. And amazingly, these companies like make these available to you and me with a completely like commercial use license, where it just you could train something on it and use it commercially. It's pretty amazing. And it's the kind of thing that's actually allowed deep learning to progress. It's one of the key ingredients, right? We have just advances in how we train the networks, how to train them deeper using things like these adaptive optimization schemes, like these normalization layers like batch norm, like fancy learning rate schedules and things like that. And obviously like the hardware, being able to do these on GPUs